Okay, number one, what is Kirchhoff's voltage law and how is it used? So here's what the voltage law says. It says that the total voltage around a closed loop is 0. Total voltage around a closed loop is 0. Now you might say to yourself, Mr. B, I don't really understand what that means. Here's another way to think about it. Another way to think about it is that the total voltage of a series circuit so basically that would be the battery, right? The battery is what provides the total voltage for the series circuit, equals the sum of the individual voltages. So, what I mean is if I have a series circuit, let's do it over here. If I have a series circuit, so here's my battery and here's my resistors. Okay? Not going to be able to write that small, whatever. If this is a voltage of 5, then maybe this is 2, this is 1, and then this would have to be 2. So that the total voltage applied for the series circuit equals the sum of the individual values. That's all Kirchhoff's voltage law says. So, connections to what we've already learned. What we've already learned is that in series, resistors share voltage. I want you to know that you know this already from the labs we've done. And that, therefore, I'm giving a name to this. So this thing here that we've said, I'm giving a name to it. It's called Kirchhoff's voltage law. So what I'm hoping you to see here in this notes is that you actually know this already. It's just we never gave a name to it yet. And so now we're giving a name to it. It's called Kirchhoff's voltage law. It says that the total voltage of a circuit is going to equal to the individual values added together. Now, the reason it's worded this way, total voltage around a closed loop, you don't actually have to have a battery to do this. But I'm not going to give you complex versions like that. Okay? For you, for your purposes, if you can say this to explain it, or you can give an example like this, or you can talk about this, that's fine for our purposes on understanding it. That's fine. Okay?
Is that like saying a pizza is like all the pizza slices out of them?
Yeah. It's exactly the same thing as that. Yep.
Isn't that obvious? Like, why do you...
Yes. It is kind of obvious for the pizza example, clearly. It's not necessarily as obvious with this unless you've done it. Like, you guys have done several labs where you've seen this, so it becomes a lot more obvious. But if you're just thinking about circuits in general, it isn't necessarily obvious that they would add up, because the current doesn't add up for series, right? The current is the same for everything. So if you're wondering to yourself possibly, well, why are voltages the same then, right? Why is the voltage for a parallel circuit always the same? I would think that those would have to add up. Well, take a look at a parallel circuit here. So why are the voltages the same? Here's a loop. Let's say this is 5 volts. 5 volts for the whole thing would have to equal 5 volts for the individual. What about the outside loop? 5 volts for the whole thing would have to equal 5 volts for the individual. That's why things in parallel have the same voltage. Things in parallel have the same voltage because they are their own loop. So in parallel, This one here?
Yeah.
This, oh, you're talking about this loop?
Yeah.
So because the current is going around clockwise like this would be a voltage drop. But see how I'm going up the down staircase here? Like current should be coming down, but if I'm making a loop this way, I'm going upwards. That would give it a negative voltage. So you'd have like -5 plus +5 equals 0, which would work.
So this is like the node rule sometimes people talk, right?
No, that's the next one. Okay, so again, I'm just giving a name to what we've already seen. Things in series share voltage. Things in parallel have the same. The reason is in series, they add up to be the total. In parallel, they're their own total, like they are the circuit. And so that's why they have the same value. Questions on the Kirchhoff's voltage law? Okay. Kirchhoff's current law. Okay? So the current coming into a node and by the way, a node is just a fancy word for a split in current. So the current coming into a node is equal to the current coming out. Okay, so if I have a parallel circuit here, what I'm saying is the current coming in, so I in, has to equal the current coming out. And a node is just where the circuit splits. So if this is I1 and this is I2, then I in equals I1 plus I2. Okay? So that's what this is saying. So what does that mean? That means that in parallel, resistors share current. This is how much current there is. They have to share it between the two of them, which we've talked about in our labs. Now you might be saying to yourself, well, Mr. B, why don't series circuits share the voltage? Don't they have splits? And the answer is no, they don't. Okay, here's the current coming into the resistor. What's the current coming out?
What's left?
Yeah. Oh, look, they're the same. There's no split. There's nothing to add. Just like up here, there's no split of voltage. There's only one resistor, so they're the same. So that means in parallel, resistors share current. In series, resistors have same current. Again, you've seen this before. I'm just giving you a name for it. The name for why this happens is called Kirchhoff's current law. So, what do you need to be able to do on the test? You need to be able to explain this concept to me. If I say, what's Kirchhoff's current law, you should be able to explain to me this idea that when current splits, it has to be divided among the splits. If I want you to explain Kirchhoff's voltage law, you should explain to me that when the voltage is used by multiple things, they have to divide it up amongst themselves. Okay? There are lots of ways to explain it. You can draw diagrams, you can use numbers, you can explain it in concepts. But you just need to be able to explain the idea to me. Now, there is a way to do it mathematically. However, I'm going to tell you right now that to do this mathematically would be a bonus type problem on the test. So we've already done this circuit. We did this circuit in the last set of notes. And what we did was we found the equivalent resistance by adding 1 and 3 together to get 4 and combining 2 and 4 in a parallel circuit. Okay? And we got 4/3 for the resistance. We found the current. We did V equals IR for the whole circuit. Here's my voltage. There's my resistance. We found the current. And we found the voltage of resistor 1 and the current because resistor 1 is in a parallel circuit with the battery, so it has the same voltage. Okay? And we found the current by doing V equals IR. What I want to show you is that you can find these other ones by doing the voltage and current laws. So for example, the current coming this way we found was 9/4. Okay? That has to split between these two ways. So 9/4 amps has to equal this current, which we already found to be 3/2, which I'm going to put it so 3/2, I'm going to rewrite it in fourths, so this would be 6/4, plus I. I'm going to call this I23 since it goes through both 2 and 3. They're series, so they would have the same current. So what's left over? Well, if it's 9/4 for the whole thing, if 6/4 is through here, what's left? 3/4. So that's the current through 2 and the current through 3 because they're in series with each other, so they have to have the same value. How do I find the voltage of them? V equals IR. So voltage of 2 equals the current of 2 times the resistance of 2. Voltage of 3 equals the current of 3 times the resistance of 3.